Hello there, minions. Let's get started on our lecture for today. We're going to do 5.1. The first section is actually going to be for getting ready, the getting ready section. This is on approximating areas. So the idea is writing out long sums of addition like 5 plus 6 plus 7 plus 8 plus 9 plus 10 all the way up to 16. That just sucks. So what we can do instead of doing that is we use it's called the summation notation or sigma notation. It's called sigma because this crazy looking E right here is the Greek letter for sigma. It's capital sigma, I believe. And the way we do it is we use a dummy variable, I, there's lots of letters we'll use, but we'll use I here. And we say what our start number is here. And we say I equals there, we put that on bottom. And we say what our final number equals over here, and we put that on top. And then we say what we're adding up, and we're adding up all our i's. So what this is telling the system to do is start at I equals 5, add that, then go up to I equals 6, add that, then go up to I equals 7, add that, and it keeps going until we get up to I equals 16, and we add that. So this is a shorthand way of writing that long summation. And we're going to take advantage of it. Summation is really like it's just shortcut for add shit up. So that's what it does. The sigma letter adds shit up. The I is called the index of summation. And like I say, when I say dummy variable, it just means any letter can work. We tend to do it on a closed interval from A to B. We go from A to B and we put our lower number down. Well, I don't know. That's not the same. Let's get rid of that. A to B is something different. Now I wish I hadn't used A to B later on. Oh well, did so here. You know what? We're going to change it. Let's change it here. Let's just write the letters start and stop. Start and stop. I don't need to put a number in or use a variable. I can just use words. A to B is something different, as we'll see. And the plural of index is indices. And so common indices that we use on these summation notations is I, J, K, M, and N, because they're just letters that aren't used that often. Until you get into higher level mathematics, but at that point you don't use this notation that much, and when you do, you're comfortable with the differences. Okay? So let's look at some practice in writing in sigma notation. We're going to write 2 to the I power, and we're going to add up I equals 1, 2, 3, 4, and 5. Let's just write out the sigma notation for that. So we're adding up 2 to the I, which means that's what we're going to put in our summation thing. And since we're going from I equals 1 to 5, this is how we would write it. That is how we write it. When it's something short like this, you're better off just doing it, though. We can add up the 5 values and we get 62. Okay? Let's take a look at another one. How could I write this in sigma notation? Pause the video and think about that for a second. See if you can recognize a pattern. And if you can recognize a pattern, what can we do with it? All right, I'll assume you did. A good way to go about it is factor the first couple and see what that pattern might be. 8 is 2 cubed, 27 is 3 cubed, 64 is 4 cubed, 125 is 5 cubed. So this might be 1 over like n cubed if we do n equals 1 to 5. Notice I used a different letter than I here. So if I did this, this should do when n equals 1. I have 1 over 1 cubed. That works. Then I have n equals 2, 1 over 2 cubed. And then I have n equals 3. I have 1 over 3 cubed. And then n equals 4, 1 over 4 cubed. And then n equals 5, 1 over 5 cubed. And if I want some crazy decimal, I'll add that up. But to keep an exact answer, I'm just going to actually leave it like this for now. I was able to get an exact answer up here pretty easy, but getting an exact answer right here, I imagine is not going to be pleasant. We could if we wanted a lot of decimal places, okay? So the rules and properties of sigma notation, we've got a few. When we have n times a constant, an example of this might be like 3n. It seems kind of weird to do n times a constant there. I'm sorry. If we have a constant and we add it up n times, we should get n times c. And if we have something different, this is literally doing, on this one, let's say n equals 5 and constant equals 2. So I'll do a little pattern here. 1, 2, 3, 4, 5. That's my i's. And what I'm adding up is 2, 2, 2, 2, and 2 for each of the 5s. That should be a 1 right there. And this ends up being 5 times 2, which is n times 2. That's what they're kind of showing there. It's not an actual proof, but that's an example. Okay. Other properties, if we have some AI, and we have a constant times it, we can pull the constant out. And there's a little walkthrough, a little proof over here on the left that I did. If you write it out, we've got CAI, and I do the i's from 1 to n. I've got CA1 plus CA2 plus CA3, and then we keep going up to CAN minus 1, and then add CAN. But at this point, I can factor out the C. And this summation this value right here is really just that sum right there. So the C is factored outside of it, and we're good to go. We can separate two of them like this. If we've got the summation of AI plus BI, we can do it like that. If it's subtracting, we do subtraction. And this is just doing like step by step here. What that's doing, let me go back to regular pen here. Let's say 1 is going from 1 to n, but m is along the way, and m plus 1 would be the next one, and then we keep going up to n. Then we can just stop part of the way through. I can break up the full summation into going up just to 1 through m and doing part of it. And then I can do the other half on another one. Or if they come separated like that, I can put them together to make them 1. That's all that one's showing. I do a walkthrough of number 4 over here on the right. If you want to see a walkthrough of number 3, it's in the book. You literally just write out AI minus BI. You plug in what the value of I is. So A1 minus B1, A2 minus B2, A3 minus B3, up to AN minus BN. At that point, group all your A's together and group all your B's together, and you can factor out the negative there. And then this one there condenses down to that, and that condenses down to that. So the different properties of summation notation. There are some formulas that go along with summation notation. If we were adding up I from 1 to n, if you actually work this out, 1 plus n up to this is really n times n plus 1 over 2. If you add up I squared, there's a formula right here, n times n plus 1 times n 2n plus 1 over 6. And I cubed has its own formula. And I'm going to say the only one you should have this one memorized. The other two are a little harder to memorize, but you should be able to know that value, like memorize that summation. It's worth memorizing, I should say. You'll see it time and time again. The other ones you'll see less and less because we get done with these summations pretty quick. Let's take a look at some examples. We are going to sum up k minus 4, that quantity squared, for k equals 1 to 100. So I'm going to write that out, and I think it's easier to expand the k minus 4 squared so that it looks like this. We go from there to there. And what we're going to do is we're going to take advantage of these two properties up here and break that summation up, okay? We're going to break that summation up to make 3 summations. And then at this point, now that we've got like a k squared here, we can use I squared here. We've got k here, we could use the I one there. And the rules for the constants is up above. This just ends up being this times that. It is important that these indices start at 1. When you're doing these formulas only work when you start at 1, okay? If it doesn't, you kind of have to add them in and subtract them. I don't think we have anything like that, though. If I do the k squared one, the k squared is doing this. So I just wrote it down, and I haven't listed what n is yet. And I'm just writing out the formulas. Then I have minus 8 times the k, because remember, we can factor out the constant. That was one of the properties up above. And I've got minus 8 times our this one right here. And then the sum of a constant was just 16 times n, where n is that value up there. N is going to be 100, so I'm going to replace all of those with 100. And I work those out, and I get a value of 299,550. Okay? Pretty complicated, but we can do it. Why don't you guys take a look at doing j equals 1 to 12 of j cubed minus j squared. Pause the video, take a look at it, see what you come up with. All right, I will assume you did. J cubed was this. That goes with j cubed. J squared and a minus was that. We did start at 1, so we're going up to 12. That will be our n. And so I'm going to replace n with 12 on all those. 12 plus 1 is 13. 12 times 2 is 24, plus 1 is 25. We got a lot of stuff going on there. You end up doing it, you get 5,434. Why don't you try finding the sum of f of x equals 1/2 x squared for 1 to 10? Here we got to figure out how we're going to do this. We can effectively use the same thing and just change this to a dummy variable. So x becomes I, and we're going from I equals 1 to 10. So we have the 1/2, the I squared formula. And the I squared formula was that. So I've got my 1/2 multiplied outside, n equals 10. And 10 plus 1 is 11, and 2 times 10 plus 1 is 21. When you work that out, you get 192.5. All right, let's try another. Find the sum from 1 to 40 of 3m minus 1. I'll assume you did it. I can split them into 2 summations. I factor out the 3 on one of them. I didn't apparently write the 1 in here. I don't like that color. There you go. And that turns into, remember, this is a constant, so constant ends up being the constant times n. And n is there, my constant is there. So 1 times 40 is just 40. And then I've got the formula for that is n times n plus 1 over 2. If you multiply this all out and add it up, you get 2,420. We'll pause the video there. That's done with getting ready. We'll make some new ones for the next section. I'll see you soon, minions.